Hey physics friends, and welcome to 16.5, which is polarization, diffraction, and redshift. We're going to talk about three different aspects of light, specifically polarization. Maybe you've heard of a polarizing filter, polarized sunglasses. What are they? How do they work? Diffraction. We've heard of diffraction before when we talk of sound, waves bending around a corner, but how does that pertain to light specifically? We'll show you some cool examples there. And then redshift. Redshift is the Doppler effect inside of light. So when we talked about before, sound changing frequency, light will also change frequency, which we call redshift and blue shift. So let's get started first of all with polarization. A lot of times when I go to a store, you'll find like polarized sunglasses. One of my favorite things to do when I go to a store and it says polarized sunglasses is like I'll take one pair of sunglasses and then I'll hold up another pair next to it and then I'll rotate that pair. Let's see if I can get this for you here. And when I go 90 degrees like this, it's like perfectly opaque. But then I go back and it all of a sudden becomes almost 50% translucent. So it goes from being pretty see-through to very not see-through. And how does that work? It turns out this is how light is actually polarized, through what's called a polarizing filter. And a polarizing filter can be thought of as like a picket fence. So if you've got a fence that's up and down, and then you take another fence and you put it 90 degrees to it, you can cut out all light. Or you can rotate that fence so that the slats line up together, and then you can let light through. And this is exactly what a polarizing filter does. Anytime light is going to reflect off of a flat surface, it becomes polarized. I did a quick Google image search for polarizing filters just to kind of give you an example of where they're handy. Fishermen use them a lot of times when looking at water. So when light is incident on flat water, it becomes polarized. So use polarizing lenses to look through that water. You can see fish where they're at. Drivers will very frequently use polarizing filters in their glasses. So when you look at windshields, it's really easy to see through a windshield when you have your polarizing filters on. Photographers will use polarizing filters quite frequently when they take pictures involving the sky, because the light from the sky has become circularly polarized. That's kind of a different subject that I don't want to get into. What is the difference between linear polarization and circular polarization? But suffice to say that photographers will use polarizing filters to bring out the deeper blues in the sky to kind of give you a more dynamic image rather than a whitewashed scene. Next, let's talk about diffraction. So in order for us, I have a video I wanted to show you with diffraction. It's really interesting. This guy, he's got a wire a really, really thin wire, and he's hung it from this post. So there's a metal post here, and there's a wire hanging down. And he's going to bring that wire, and there's a green laser. You can see the green laser spot. He's going to bring that wire into the green laser spot. And you might think that it's going to create a shadow on that. It creates something much different. Let's give a look.
But in fact, that's not what we see. Let's take a look at what actually happens. So I'm going to slide the wire across, and you need to be quite careful to get it. There we go. You should just be able to see here where the laser is shining over the wire. And on the screen, oh wow. If you look at the spot, you should be able to see that there's no dark line down it at all. It's still perfectly bright. But on either side of it, you can see bright and dark bands extending out many times the diameter of the wire or the laser beam. So the question is, how do you relate this pattern to the wave nature of light? Well, light waves travel from the laser over to the wire, and they diffract around each side of the wire. That is, they're bent to fill the space beyond and behind the wire, extending over to the screen. So in this region, we observe interference between the light waves that have come around one side of the wire and around the other. Where the waves are in phase, that is, where the crest of one wave matches the crest of a wave that's come around the other side of the wire, we observe constructive interference. And that's what leads to these bright regions on the screen. And it's what explains the absence of a shadow in the center. In this region, we've got constructive interference from light which has traveled around each side of the wire, because this point is exactly equidistant from either side of the wire. We also observe destructive interference. That's where the light traveling around one side of the wire interferes destructively with the light that's traveled around the other side of the wire. And that's what leads to the pattern we see on the screen. Now, it's easy to get lost in the maths and the
alternating bands of constructive and destructive interference as the light kind of interferes with itself. I took some pictures. So this is, you've seen this before with waves up here, how the waves, when it goes through an opening, it will bend. And if you have two openings, it will start interfering with itself. So that light traveling around each side of the wire, you end up with an interference pattern that you saw at the bottom. Maybe you've blown bubbles before and you really look at them a little bit close. Or if you've spilled oil on water and you notice that it makes this rainbow pattern. Or if you look at the bottom of a CD or DVD, this is called thin film interference. So this film is very, very thin, and it's fluctuating in its thickness. So when light is incident on the surface, some of the light will reflect off the top surface. Some of the light will transmit through, reflect off that change in medium, and then bounce out. And then these two waves are going to interfere with each other. And so you have this ability to look at, and this is telling you the thickness of the bulb at different, of the bubble at different spots, because the light is interfering with itself as it reflects off the different sizes or different thicknesses of the film. Redshift and Blueshift. I've got another video to kind of explain that too, so bear with me.
The world is said to be a big place, but the universe is much bigger. And what's more is it's expanding all the time. How do we know this? Because of the evidence provided by Redshift. In this video, we're going to learn about Edwin Hubble and his use of the Doppler effect as evidence of an expanding universe.
Maybe you've heard of the Hubble Space Telescope. It was named after Edwin Hubble. Let's learn how he's so important.
Before the work of Edwin Hubble, scientists believe the universe was a lot smaller and static. Edwin Hubble became a famous American astronomer after he examined the light from nearby galaxies. The atoms of elements that are in the atmosphere of a star absorb specific wavelengths of light. This can tell us the chemical makeup of the star, as well as its relative distance from the Earth. We can see the absorption of these different wavelengths when looking at the light spectrum of a star, also known as Fraunhofer lines. The black lines show us where light is being absorbed. We can tell the exact wavelength of light being absorbed. The Doppler effect is the observed change in wavelength and pitch of sound, or change in wavelength and color in light if the source is moving relative to the observer. Have you ever heard a police car pass and noticed the sound of the siren change suddenly? Then you have experienced the Doppler effect. The same thing happens to the light of the stars traveling to us from distant galaxies. When a star is moving away, the light from the star, because of the Doppler effect, is of a lower frequency than expected. It moves towards the red frequencies, redshift. Hubble noticed that most of the galaxy's light was shifted towards the red end of the spectrum, and also the further away a galaxy was, the more its light was red-shifted. Look at these two atomic spectra, one from our Sun and the other from a distant star. Remember, low-frequency visible light is red and high-frequency visible light is blue. The lines in the spectra are the same pattern, but they have been shifted to the red end of the spectrum of the distant star. Hubble concluded that most galaxies were moving away from our own. The further away a galaxy was, the faster it was moving away from us, and the universe is expanding. Look at these three spectra. Which of these stars is closest to us? Which of these stars is furthest away from us? Redshift also provides evidence for the Big Bang Theory. You can find out more about the Big Bang Theory in this video. So that's how we know the universe is a big place and expanding all the time.
If you liked the video, give it a...
So the importance of Hubble was when he looked up at the stars in the sky, he noticed that everything was moving away. And not only that, it seems like the farther away a galaxy was, the faster it was moving away from us. So either we're in the exact center and everything is moving away, or the universe itself is expanding. And this gave rise to the expansion of the universe. And it turns out that everything is moving away from us, except for the galaxy Andromeda. That's coming towards us, and it's on a collision course with the Milky Way, but not a big deal. Nothing will touch when these two galaxies merge. So, the Doppler shift. Redshift and blueshift is just examples of the Doppler shift of light. If something is moving away from you, it stretches that wave out and makes it look redder. And if it's going towards you, it squeezes that wave together and makes it look bluer. So they were talking about atomic spectra, and you can tell that if it's shifted towards the red, it's moving away. If it's shifted towards the blue, it's moving towards us. I wanted to just make a quick stop on where this spectra comes from. This is actually our sun. Like if you were, we think that the sun has a rainbow, but there's actually holes in the sun's visible spectrum, like literally wavelengths that it doesn't give off. And for a long time, this confused a lot of people as to why this was. And it turns out this is due to what's called quantum mechanics. So you can have what's called emission spectra or absorption spectra. So you can take, let's say, hydrogen and you excite it and it gives off certain frequencies. Or if you pass white light through hydrogen, hydrogen will absorb those exact same frequencies. So you have what's called absorption spectra, where it will absorb, and this is what you're seeing on the top, absorption. White light, it will absorb certain colors. And then if you were to excite hydrogen and then spread it out, you'll get these colors right here. So this is how we're able to tell how far away stars are and what the star is made of, just by taking its light and passing that light through a prism and looking for the telltale signs of different elements. Why do they do that? This is a quick intro to quantum mechanics right here. So when an element goes from one energy level to another, it gives off a photon. So right here, for instance, if the electron from hydrogen goes from like the n equals 6 energy level down to n equals 1, it gives off a 400 nanometer light, which is blue, because we see between 400 and 700 nanometers. So all of these different photons are visible to us, and this is where you get the spectrum from. This, what we call quantum mechanic, it only goes from one energy level to a certain one. You can't get energy levels in between. There are certain energies that we can't see. This is definitely too high for us. These wavelengths are really tiny, and these are ultraviolet or even maybe X-ray. Or you can have ones too low for us, and these are infrared. So it's giving off all sorts of light, just certain ones that our eyes will see. We call these the Balmer series, and there's ones that are too high, ones that are too low. How do we actually calculate? How do we use the Doppler shift when calculating the light? So here's a couple of example problems. I wanted to write down here. These are the equations that we're going to be using as we're going through this Doppler shift one here. I don't like the way that the book writes it. Is equal to the wavelength plus or minus v, the velocity that you're moving, and then c stands for the speed of light, 3 times 10 to the 8th times your original wavelength. Here's our first example. Example 1. You are pulled over by the police for running a red light, and the wavelength of red is 700 nanometers. How fast You were traveling and it looked green to you, 550 nanometers. How fast must you have been traveling to do that? So here, there are two equations. The wavelength observed is equal to wavelength plus or minus the velocity over the speed of light times wavelength. And then there's another one that deals with frequency. So the frequency observed is equal to the frequency 1 plus or minus v over c. Now, because this is dealing with wavelengths, I'm just going to plug it right into this equation. I could change this into frequency and then use the bottom one, but I'm not going to do that. I'm just going to use the top equation because I've been given wavelengths. So the wavelength that I observed, it looked green to me. So I'm going to put 550. Now you don't have to do nanometers here. As long as you put, let's just take off 9 zeros from here. And as long as we do it to both sides of this equation, we're going to be okay. How fast was I going? Times this wavelength 700. Now, again, as long as we do the same thing to both sides, we're going to be okay. Now, this velocity is going to be meters per second, and the speed of light is going to be 3e to the 8th. And that's also meters per second. So I just do a little creative math. 550. I'm going to subtract 700, so I get negative 150. Now I want my wavelength to go down, and the only way to make that go down is to choose this to be negative. So this has to be negative when I go to do this problem. So that is going to be negative v over 3e to the 8th times 700. So then I multiply by 700, and I'll divide also by negative 1, and it's like 0.21 equals v over 3e to the 8th. Now, I'll bring the 3e to the 8th over, but I'm just going to leave the 0.21 out front for right now. So here's what this means. How fast was I going? I was going 21% of the speed of light. A lot of times people will just do that. They'll say 0.21 c was my velocity. You could multiply that out as well. And if you take 0.21 times 3e to the 8th, you get 64 million meters per second. Either one of these answers is an acceptable answer to explain how fast you're going. That's really, really fast. I mean, and if you do go that fast, red will look green if you're traveling towards it. All sorts of other stuff happens to reality around you as you're going that fast too. But suffice to say, you can leave it as 0.21, or you can say 64 million meters per second. The last problem in the example. The sun rotates differentially, meaning that the equator of the sun actually rotates faster than the edge. So hydrogen, the equator takes 25 days to rotate once. The diameter of the sun is really big. The major component of the sun is hydrogen, and one of the emission frequencies is this. What frequencies would you expect from each edge of the sun as you observed it? So on this edge, as this was going towards you, it would look blue, and on this edge, as it's moving away from you, this would look red. So the question wants to know, what frequencies are you going to see as it's moving towards you, and what frequency are you going to find as it moves away from you? So we're going to use that equation that involves frequencies. Frequency observed is equal to 1, or the frequency, 1 plus or minus v over c. So our first order of business is figuring out how fast is this traveling. What's the velocity of that equator? And my velocity, it's distance divided by time. And it's not that straightforward. The distance that it travels is a circumference. So this sun, it's a circle. So the circumference, it's 2 pi times the radius, or pi times the diameter, and they gave me the diameter. So I'm going to take 1.4 times 10 to the 9th. I'm going to multiply by 3.14, or pi, and you end up with 4.4 times 10 to the 9th meters. So that's the distance that it travels, 4.4 times 10 to the 9th meters. How much time does it take? It says it takes 25 days. So it takes 25 days to make that journey. So the time, 25 days, I'm going to convert that to seconds. 1 day is equal to 24 hours, and 1 hour is equal to 3,600 seconds. So when I do a little dimensional analysis here, that ends up being 2.2 million. So 2.2 times 10 to the 6th seconds. So 2.2 E6. Now, 4.4 divided, I can figure this out right now. 4.4 divided by 2.2 is just 2, and then 9 minus 6 is 3. 2 times 10 to the 3rd, so 2,000. That's your velocity. 1 plus or minus 2,000 over 3e to the 8th. What frequency would you expect? So we're looking for the frequency that we observe. And the frequency that is actually there, you can't see it, but it's 4.57 times 10 to the 14th. So I'm going to run this equation through once with the plus sign, and that's going to tell me my frequency go up, and that's going to give me the blue side. And then I'm going to run this equation once with the minus, and that's going to make my frequency go down, and that's going to give me my red frequency. So doing this, running it in my calculator, running these through, you get a really, really small change. It's 4.57003. So it went up a very small fraction, and then it went down that exact same small fraction as it was going towards and away from you. And this is literally how we look for alien life form. Alien life is, we're searching for it right now using this exact idea that if there's a star, and I've got a star here, and it's got a planet around it, as that planet exerts pull, it creates a wobble in the star, and then we just look to see some sort of sinusoidal pattern in the red and blue shift, and then we can tell it does have an alien planet around it. We can tell how big, we can tell how far away it is, its orbital period, and so on. Thanks for hanging with us today. I appreciate you paying attention.